All right, so my name is DallinJones, and my project is on using open source Python scripting to update fire perimeter datasets for the USGS. As wildfire intensity and occurrence increases in the United States, especially in the West, there's become a need for a comprehensive dataset to access historical and present fire perimeter data for a wide variety of ecological analyses. While possible to collect this data, it was difficult to track down the required data collection from a wide variety of federal and local agencies. In 2021, researchers from the USGS's Forest and Rangeland Ecosystem Science Center filled this need with the combined wildfire dataset. This dataset includes vector and raster fire perimeter data from 1835 to 2020 and contains over 524,000 fire perimeter polygons. While this dataset is a great comprehensive resource for fire perimeter data, the methods used to create this dataset produce inaccuracies, especially if fires close together and in the same calendar year. In the original script used to create the dataset, in order to clean it up, smaller fires within 500 meters of larger focal fires were dissolved into the larger fire. While this method was effective in eradicating duplicates, this methodology can cause inflating of polygons as well as eliminating smaller fires altogether. So kind of the goals of this project were to build off the original USGS script and create a new script that increases accuracy of fire perimeter polygon identification by using a decision tree methodology. Another goal was to integrate the script with the current USGS script and then later come to find convert the ArcPy code to open source or GeoPandas. And since the original script was created using ArcPy, it required anyone to have necessary access to the proprietary software. So I wanted to change that to all open source so anyone could access that. And then the final goal of the script was have the script ready to create the new combined wildfire dataset. To complete this project, I used the following workflow. I selected areas of interest and then pre-processed the data to get ready to implement in the script. Chose decision tree parameters, set up the Python environment, and then the meat potatoes of the project kind of created the code using the decision tree parameters, and then tested those areas of interest on the code that I've written. Then the next step was to repeat the workflow in ArcGIS Pro, and then conduct an accuracy assessment comparing the two workflows, and then integrate the code with the current USGS code, and then finally dataset creation. So the data used to create the scripts were the combined wildfire dataset that I mentioned earlier, as well as the fire occurrence dataset from the USDA. The combined wildfire dataset was the main focus of this project and includes three different layers. The combined dataset, which is the raw polygons that are unmerged. The merged dataset, which is the combined dataset after it has been ran through the previous USGS code. And then there's also a rasterized dataset from the merged layer that was used to visualize different metrics, but I didn't use the raster layer for this project. And then the fire occurrence dataset is an ignition point dataset maintained by the USDA. And this dataset was used as a factor in the decision tree process, which I'll go over later in the presentation. So selection of the study areas or area of interest was determined by the scale of the fire as well as different types of overlaps. This was done so I could test the code with a variety of different scenarios. The first area of interest chosen was the Soda Fire Complex of 2015. This area is located in the Wahi Mountains in southwestern Idaho, and the fire area covers 334,980 acres, and the main fire burned for almost 3 weeks before containment. The second AOI chosen was the Bruno or Cat Fire Complex of 2018. This fire is located in south central Idaho by the Nevada border. The fire area covers over 1 million acres, and the main fire burned for about a week before containment. So to create appropriate parameters to determine the distinct fire perimeters, separate from the large focal fires, the code would follow a decision tree to make the determinations. To choose the parameters, I set up panel meetings with wildfire ecology experts from the Forest and Rangeland Science Center, as well as the Missoula Fire Center, and as well as Boise State University as well. Their expertise was critical to kind of creating a decision tree as a whole. The resulting decision tree contains 3 branches that all start with using the GeoPandas intersect tool. So the first branch is the large overlapping branch. Fire perimeters that highly overlap the focal fire are inputted into this branch. The polygons then go through a series of functions that compare attributes such as ignition date, fire code, as well as finding the presence of the ignition point data from the fire occurrence data set that I talked about earlier in the presentation. The polygons are either dissolved into the larger focal fire, as done in the previous script, or determined to be a distinct fire. Distinct fires are placed into a final geodata frame that is later transformed into a shapefile or geopackage, or even an Esri geodatabase, as determined by USGS later on. The second branch is the using small overlapping polygons are inputted into the small overlap branch. Similar methodologies are used to determine if the polygons are distinct or dissolved back into the focal fire. Fires in this branch were also either dissolved into the large focal fire or put into the final geodata frame. The third branch were polygons that do not overlap the focal fire at all are run through this branch. More evidence was needed to dissolve these polygons back into the focal fire. To create the script, Python 3.7.11 was used due to versioning issues with different libraries. An Anaconda environment was set up to using open source software Anaconda to manage the different Python modules. Spider was my preferred IDE for this project for its ease of debugging and variable and plot visualization. GeoPandas was the main module used for the spatial data manipulation and iteration, but its dependencies, pandas, as well as Shapely were pivotal to making the script work as well. Matplotlib was also used for testing and visualization purposes as well. So once the script had been created, it was tested on the AOIs mentioned earlier. For the soda fire area, the original layer had 157 different polygons. Most of them were duplicates from different agencies inputting the same fire. This was trimmed down to 34 distinct polygons once it was run through the script I created. In total, this area took about 3 minutes to run through the decision tree. The map shown shows, on the left, it shows the merged layer from the USGS's script, and then on the right shows after running through the decision tree script. For the Bruno study area, 59 of the original polygons were trimmed down to 8 distinct polygons. Again, most of them were duplicates from entry error. And this area took under 2 minutes to run through the decision tree script. To make sure that the script was on the right track to perform the decision tree manually in ArcGIS Pro, using tools such as intersect, buffer, and I think also select by location, instead of in the script using the GeoPandas functions. While this process was long and tedious, it produced similar results that were put into a confusion matrix in Excel. As you can see in the chart, the Python workflow for the soda fire complex dissolved 122 polygons and created 35 distinct polygons, while the ArcGIS Pro dissolved 120 and had 37 distinct polygons, so a 2 polygon difference. For the Brunel and Cat Fire complex, it produced the same results with the same number of polygons getting dissolved. So once the code had been tested with high accuracy, it was integrated into the USGS script. This was not possible at first due to their use of ArcBay and GeoPandas dependency issues, but this kind of worked out into my favor, so I was able to change everything to open source instead of relying on Esri software. In total, the entire script, including all the functions, combined for over 1,600 lines of code. Once the completed code was integrated, then it was uploaded to a GitHub repository for easy access from my paper, as well as easy access and manipulation on the USGS's end. The next steps in the script is for the USGS to run it on their supercomputer on all polygons for all used in the dataset. Using the supercomputer will decrease the script's runtime. I think originally, without the decision tree, it took the programmer a week of computing time. As you can imagine, each fire takes 2 to 3 minutes currently, so multiply that by how many, the thousands of fires from 1835 to 2020, that's going to take a long time. So the supercomputer will definitely help in that process. Some of the biggest takeaways of this project was more on the management side, setting up meetings that work with everyone's busy schedule, especially on the government side, proved to be difficult, as well as making sure that everyone's on the same page and making sure that the code that I'm writing is kind of what they were envisioning. So that was kind of the biggest takeaways that I had from this project. And well, the script was successful in increasing accuracy of the future data set. This script also gives more user customizability through the use of open source, and users will be able to easily access the code and manipulate the parameters to fit their needs. All right, any questions?